First, binomial distribution, its mean comma variance, and also Poisson distribution, mean comma variance. So we have two other theorems here under the concept called mathematical expectation. We know that we have two types of random variables called discrete random variable and continuous random variable. Okay, two types of random variables, discrete random variable and continuous random variable. Mathematical expectation we write with E of x, which we read as expectation of x. So this expectation is going to have two forms depending upon the nature of the random variable. If it is discrete random variable, this expectation is being replaced with x, and within the brackets we have x, we write that, and followed by its PMF. You know that for a discrete random variable we will have probability mass function. For a continuous random variable there is a probability density function. So expectation of x is equal to, if it is in case of discrete, that is when x is a discrete random variable, we replace x with sigma, within the brackets x we have, and its PMF p of x. If at all this is a continuous one, we start with integral x into the corresponding PDF. So this is the one when it is a continuous random variable. Now this is the case when we have a one random variable. Whenever we have two random variables, that is, let us say that we have two random variables x comma y. So then expectation of xy will be, okay, so one variable means we are writing only the PMF of one variable. If it is a discrete random variable, as we have two random variables, you will get two sigmas xy within the brackets, and not p of x, p of xy. This p of xy is nothing but the joint PMF. Try to understand the difference. The previous one is the one when we have one random variable. When we have two random variables, say comma x comma y, where both are discrete type. So as we have one variable, we have started with one sigma. If there are two variables, we will start with two sigmas, one with respect to x, one with respect to y, and within the brackets we have xy, and not p of x, you will write p of xy, which is nothing but the joint PMF of both xy. If it is the discrete one, you will write f of xy into f of x comma xy into f of x comma y, where f of xy is the joint PDF. Moreover, to discuss the two theorems on in mathematical expectation, you should know that whenever x comma y are independent, as we have two random variables, we will have two cases called when they are independent and when dependent. When they are independent, f of xy is equal to f of x into f of y, where this is the joint PMF PDF is equal to, the joint PDF is equal to product of the marginal PDFs. Marginals means individuals. Whenever they are independent variables, the joint PDF can be written as the product of the marginal PDFs. Marginal means for x separately, y separately. When they are dependent, you cannot write those two as f of xy is equal to f of x into f of y. So these are the definitions for expectation in case of one variable univariate, for bivariate in case of two variables when they are independent. These three are necessary to discuss the two theorems called addition theorem on expectations and multiplication theorem on expectation. Addition theorem on mathematical expectation. So let us say the statement, let x comma y are any two variables, random variables, then show that expectation of addition means we are going to separate the two variables with plus. E of xy is equal to E of x plus E of y. Again I repeat the statement. We have two theorems on mathematical expectation, one called addition theorem on mathematical expectation, multiplication theorem on expectation. So the statement here is, if x comma y are any two random variables, either they may be discrete or continuous, whatever may be the variables, you need to show that the addition theorem states that E means expectation of, addition means plus, E of xy is equal to to E of x plus E of y. You need to show this. So how many variables? To start the proof of this, let us recall that definitions of expectation. Let us discuss this with these with continuous random variables, both addition and multiplication theorems. They may be either discrete or continuous. So if you deal with the discrete continuous case, the proof will be easy. So before going into the proof of the theorem, so let us again redefine the expectations in case of continuous. So expectation of x, how many variables are there? One variable. So as to resolve this expectation, if it is a continuous one, as we have one variable, you will start with integral. Within the brackets we have x into the corresponding PDF. Similarly, if y is another variable, how do you write? Again we have one variable, only one integral. Within the brackets we have y into f of y dy. Similarly, E of x plus y. E of x plus y will be, as we have these three terms in the statement called E of x plus y, E of x comma E of y. Let us define all those before entering into the proof of the theorem. Let us define what is E of x plus y, E of x, E of y. E of x plus y here means how many variables are there we have within the brackets? Within the brackets we have two terms or two variables. So you will start that with integral. Am I right? How many integrals? Two integrals. Within the brackets we have x plus y. So write down the same. So as we have only one variable here, you wrote the corresponding PDF. As we have another variable y here, you wrote the corresponding PDF. But here within the brackets we have the variable called x plus y. So as we have two, you should write the joint PMF. Am I right? Observe the difference here. E of x is nothing but, you are resolving the expectation in case of continuous one. Continuous means you know that E going to replace with integral. Within the brackets we have x, only one variable. So you will write x and its PDF dx. Similarly E of y. Coming to this, we have two variables. Means x and y are the two variables. So you will get two integrals, and within the brackets we have x plus y. Not simply you cannot write f of x or f of y because we have two variables here. So you should write the joint PDF. This is the expressions for e of x, e of y and e of x plus y. Now one more thing, try to understand. What are you calling f of x as? PDF, probability density function of x. F of y as probability density function of y. F of x plus y is nothing, f of x comma y is nothing but joint PDF of x comma y. What are these three here? F of x is the PDF of x, PDF of y. XY means joint. As we have two, we use the word called joint. Joint PDF of xy. So how do we get, what is the relation between f of xy and f of xy and f of x, and f of xy and f of y is nothing but, if you integrate, means if you integrate joint PDF with respect to y, you will get the marginal PDF of x. I am explaining the relation between these three. See, this is joint, means we have two, these are individuals. So we observe that this is a super and subset. So we can obtain f of x from joint, you can obtain f of x. Similarly, from the joint PDF of x comma y, you can obtain the PDF of y. Then how to obtain those? So you have this, is you are calling this as the joint PDF of x comma y. Then if you eliminate y, you will get x. Then how to eliminate y there? Eliminating is not simply by subtracting. If you integrate this with joint PDF with respect to y, you will get the joint PDF of x. Similarly, if you integrate the joint PDF of x, means you are eliminating x, then you will get the PDF of y. So these are the two ways how we get the joint PDF of x comma y from individual PDFs from joint PDF. So what you need to prove, all these are nothing but introduction to prove that one, the addition theorem. I think this is the one you need to prove. Am I right? So again you consider the LHS. What is the LHS here? Expectation of x plus y. So how can you write this, how can you resolve this expectation? As this is the expectation and you are discussing continuous one, you should start with integral. Moreover, we have 2 here, so try to place 2 integrals. And within the brackets we have x plus y, write the same. As this is the, we have 2 variables, we are going to write the joint PMF. Now I want to separate that as, we can multiply this double integral. I think we can write x into f of xy dx dy plus y into f of xy dx dy. Can I write in this way? And let us take these integrals for both the terms. So double integral x f of x f of, I think this is the first term, now one integral with respect to x, one with respect to y. So we have considered the LHS to get the expectation of x. Okay, so if you, what I said, if you integrate the joint PDF with respect to x, you will get f of y. If you integrate the joint PDF with respect to y, you will get the PDF of x. Means eliminating from joint, if you remove x, you will get the PDF of y. From the joint, if you remove y, you will get the PDF of y. Then how to make this removal is nothing but not with minus, with respect to integral. So if I write in this way, I think we can write in this way. What I did here, I have separated, I wrote here integral x dx separately and integral y f of xy dy separately. So if you observe this term, you are integrating the joint PDF with respect to y. Means you are removing the effect of y. Then which PDF you will get? You will get the PDF of y. So this is nothing but x dx. This is f of x. Plus here also I want to write y as and y dy integral x f of x comma y dx. So what I said, if you integrate with respect to x, you will get the, means you are removing the effect of x, then you get the PDF of y, integral y f of y. So I want to rewrite that. So we have started with expectation of xy, we got integral x f of x dx, integral y f of y dy. I think we can write this as expectation of x, this as expectation of y. How can you write expectation of x? If it is a continuous one, expectation is going to be replaced with integral. Within the brackets we have x. As this is the one variable here, we will write the PDF called f of x dx. Plus similarly, integral we can replace with x. Within the brackets y we have. So this represents expectation of y. So we got expectation of x plus y is equal to expectation of x plus expectation of y. Okay.